Hello, Honors Higher Algebra students. This is Mr. Johnson, and this is the first lesson in linear programming. And we're going to be looking at writing and graphing linear inequalities. So first, we need to talk about our symbols. So we have greater than, which is our very first one. You guys have seen that before, greater than or equal to. So we have this little equal bar underneath, less than or less than or equal to. You probably learned about these back in early or mid elementary school. You might have even, I remember a teacher of mine in elementary school talking about an alligator eating the bigger number or something like that, or some animals trying to make it fun like that. So anyway, these symbols we've been looking at for quite a while, and we're going to be using these now ultimately with two variable functions, but we'll look first at single variable functions. Here's our first example. We have more than 10 people in line. So that means that if x is the number of people in line, x would be greater than 10. So it cannot equal 10, but it must be more than 10. So let's say that this was 10 on our number line. We would graph this by putting an open circle because we're not including 10, but we would shade everything that was larger than 10 in that direction. In other words, we're really close to 10. We're infinitely close to 10, but we can't touch 10, but we want any number that is larger than 10. Let's say that there are at least 10 people in line. Let's use the same variable. So we have x is greater than or equal to 10. Now we're including 10, and so the difference obviously is that now 10 has a closed circle because we're including it, and then of course we would shade everything off to the larger values of 10. So anything that is 10 or larger. Let's say that we have what's called a compound inequality. So now we have a situation where a person has tickets that are available for a concert and they're in row 10 or above, but less than row 40. So in other words, we could include 10, but we don't include 40 and we are less than 40. So you could almost think of this as in one case, we have x is greater than or equal to 10, and in the other case, we have x is less than 40. But we put these inequalities together, we call it a compound inequality, so that we can represent x in between these restrictions. Now we can include 10, but we can't include 40, and so it's in between these. And let's assume that our scale is kind of set, and I'm just going to pretend like that first one is 10. I'm going to put a closed dot there. I'm just going to say that this last one is 40, so I know that it's not necessarily a nice scale, and that's going to have an open circle, and then everything is shaded in between these two, and that's how it would look to have some sort of compound inequality. So let's move on to two variables, because that's what we're going to primarily focus on here, and it's really a connection to that single variable inequality that we just talked about on a number line. But now we're going to look at a plane. We're going to look at how to shade a plane that would consist of two variables. So let's say that your mom went to the grocery store to buy jelly beans. She wants less than 5 pounds of strawberry flavored jelly beans and at most 2 pounds of lemon flavored jelly beans. So we have two different variables. We have strawberry and we have lemon. X is the number of pounds of strawberry jelly beans, and Y is the number of pounds of lemon jelly beans. So what are the inequalities that would represent the situation? So one of the tasks that we're going to be faced with in this unit is going to be how to write our equations to represent our variables. So if X is the number of pounds of strawberry jelly beans, and it says that we want less than 5 pounds of strawberry jelly beans, X would be less than 5. If Y is the number of pounds of lemon jelly beans and we want at most 2, then Y would be less than or equal to 2. So here we have our two inequalities. X cannot include 5, but it can be less than 5, and Y can include 2, but it's also less than 2. Okay, let's graph our first one. So we're going to graph X is less than 5. And remember, you can't include 5, which means that on your plane, you go to X is 5, so 1, 2, 3, 4, 5. That's about right here. and we would represent this with a dashed line. That's kind of the equivalent of that open circle on the single variable number line. We have a vertical line where x is equal to 5. However, since x is less than 5, it can't contain anything on 5. But we're going to be shading in this region where x is less than 5. So anything that I'm shading right now is a possible solution. So what that means is that, let's say that you wanted to pick out a point here. Let's say we pick out the point, I'll grab this one. This is going to be x is -2 and y is 1. So the question is, does that point satisfy the inequality? So if we were to substitute this in, we have nowhere to put y. So y doesn't really matter in this inequality. We just look at x. So the question is -2, actually, let me write it this way, is -2, so that's my x value, is that less than 5? The answer would be yes, of course it is. So that satisfies the inequality. If you were to pick, let's say, this point right here, 1, 2, 3, 4, 5, 6, 7, 8, and -1, if we were to test this, is 8 less than 5? The answer, of course, is no, and that's one of the reasons of many of why that's not shaded. So anything that's shaded, any point you could ever think of, whether it's a decimal or not, is going to work in this particular inequality. Now let's say that we pick a point on the line. Let's say we pick this point where x is 5 and y is 3. So the question is 5 less than 5? And the answer is no. And that's why that's a dashed line, not a solid line, because nothing on the line could be a solution to the inequality. Now we'll take a look at the lemon jelly beans. So this is going to be y less than 2. So we find y equals 2. Y is less than or equal to 2. So we find y is equal to 2, which is a horizontal line. So this represents always y is 2. That's going to be solid because y is less than or equal to 2. And now we shade any values of y that are less than 2, which would be anything, sorry, that's a little bit sloppy, anything in this particular region. And we could do the same thing. We could say, all right, we're going to pick a point. Let's pick the origin. So we pick 0, 0. There is no place to put x because the equation doesn't have an x in it. But the question is, if y is 0, is that less than or equal to 2? And the answer to that is yes. What if we were to pick another point? Let's say we pick this one over here, which is 1, 2, 3, 4, 5, 6, 7, 8. And -1. So obviously we don't have any place to put x, but if y is -1, is that less than 2? And the answer is yes. So that's working. Okay, let's pick a point here on the y-axis, which means x is 0 and y is 1, 2, 3, 4. And so the question is 4 less than or equal to 2? The answer, of course, is no, and that's one of the reasons why that isn't shaded. So anything in the shaded region satisfies the inequality. Okay, here's a nicer look at both of them together, okay? And so this is the x less than 5 graph that I already showed you, the y less than or equal to 2 that I already showed you, and we have both shaded. The region where these are shaded and overlapping right here, that is called the feasible region, or all of the possible solutions that satisfy both. So what we're going to be looking at in this particular unit is to take a look at multiple graphs and where they overlap, and we're trying to find this feasible region. Let's try this inequality. Now the way that I always do this is to write it in slope-intercept form because I think it's just a little bit easier. So if you were to subtract x and add y, I'm just going to rewrite this. Y is greater than or equal to 4 minus x. This is easier for us, I think, to think about. So this is going to have a slope of -1 and a y-intercept of 4. That's one way we can do this. So we have 1, 2, 3, 4, and a slope of -1. So you can plot some points along here if you want. I'm going to show you another technique to graph these in a little bit. Now this is less than, this is y is greater than or equal to, which means that we want to make sure that this is a solid line like this. and y is greater than or equal to, which means we need to shade values for which y is greater than. For some of you, it's really easy to see this. It's very simple for you to grasp where to shade. Obviously, we have two options here. We have this option, or we have this option. And for others of you, it can be really confusing, especially with a slant line like this. So one of the ways that we can do this and sort of have a foolproof way of figuring out where to shade is to test a point. The only issue is you don't want to test a point that's on the line, because then it's going to be really confusing. It's not going to help you. So for instance, 0, 0 is not on the line, and 0, 0 is a really easy point to use. So I'm going to test this. So I have 4 minus y, remember y is 0, is less than or equal to x is 0. And my question is this true or false? So if I just simplify this down, is 4 less than or equal to 0? The answer is no. Well, the beauty of an inequality like this is that if a point like 0, 0, for example, doesn't work, then I must shade the opposite side. If 0, 0 did work, well, then I would have to shade that side. It's an all or nothing thing. It's not like I pick a point and it works, but other points in that same region don't work. If this is region, let's say this is region A down here. This is region A and this is region B. Every single point must work in each of the regions for you to shade it. So for example, I picked a point in region A, it didn't work, which means that none of the other points that I would pick work. So even if I picked a point over here, whatever that point may be, that point will not work because they all either have to work or none of them work. So if we were to pick a point in region B, let's say we pick this point, 1, 2, 3, 4, 5, 6, 7, 8. So I pick 8, 0. Well, then I need to test this. 4 minus y is 0 is less than or equal to 8. So is 4 less than or equal to 8? And the answer, of course, is yes. So you can pick any point you want that's not on the line, and it allows you to know where to shade. Now, again, there are many of you that can see this equation right here, and it says y is greater than or equal to, which means that you know you need to shade above the line. But again, for some of you, that's going to be a little bit tricky. So this is just a technique for you to know how to do that. All right, we're going to take what I just gave you, which is now here in the red and the pink there with the shaded region, and I'm going to include x is less than or equal to 6. So I'm going to change some colors here. So x is less than or equal to 6 means that we have a solid line. So solid line, and x is always 6 along that line, but x is less than or equal to 6. So it's much easier to shade a vertical or horizontal line because you're just picking values that are less than it, which is off to the left side. The slant lines can be sometimes a little more confusing. Okay, so obviously it's all of this stuff that we're including in our solution. And I'm just going to go to the next slide, which will show them nicely set up together. Okay, so here are the two inequalities that we have, and we're going to add one more to this mix. This one is, let's see, I'm going to have to pick maybe green. Okay, this is already set up for me in slope-intercept form. So my slope is 1, and my y-intercept is 8. So I'm just going to graph those. So I have 8, my slope is 1. So again, you can plot some points in here. One of the things that we're going to really want to make sure to identify are the points of intersection. So I want to make sure that I know exactly where this new line is going to intersect the red and the blue. Now this one is y less than, which means it's dashed. So I'm going to dash this line. And I do have my points of intersection that I've been able to identify just by plotting the slope there. But then we have to shade this one. So we can do a similar approach. 0, 0 is not on this particular line. So if we test 0, 0, if y is 0, the question is that less than x being 0 plus 8? So is 0 less than 8? And the answer is, of course, yes. So since 0, 0 worked, I'm going to shade the region that contains 0, 0. And again, for those of you that kind of have a visual sense of this, it makes a lot of sense that we would shade below this line, and that would include the point 0, 0. So it looks like this. I'm going to go ahead and go to the next slide, which will show a nicer picture of all of that. Okay, so here we have all three of our constraints. Okay, so this is some of the vocab that we have to be able to identify. So our constraints are all of the inequalities. So we have y less than x plus 8, that is one constraint. We have y is greater than or equal to negative x plus 4, that's another constraint. And we have x less than or equal to 6. Those are the three constraints in this particular problem. The feasible region is going to be this triangular region. I'm gonna, actually, you know what I'm gonna do is draw this just like this. So it looks like that. Oops, this is not a very good picture. And I'm just gonna put in my vertices, which is the next part. So my vertices will be 6, negative 2, and this one will be, let's see, that's gonna be 6 and 14. And then this one over here is negative 2 and 6. And that's my feasible region. And remember, the feasible region is just simply the overlap of all of your constraints. And you can see that over here. I know that the graph is getting a little bit messy with all the colors. So those are my vertices of the feasible region, and the shaded feasible region in black there, where all of them overlap. Let's try another example of this, putting all of this together. So we have x is greater than 1, greater than or equal to 1. So we have a solid line right here at x is equal to 1, and we're going to shade greater than or equal to 1, which means that we're going to shade over in this region. It's really important to try to stay nice and neat with these graphs because they get messy pretty quickly. Y equal to 0 is, of course, the x-axis. So we have a solid line here on the x-axis. That's y equals 0. And then we're going to shade this for y greater than 0. So that's, of course, above. I'm sorry. It's going to shade like this. So far, you can see really clearly that we have an overlap between the red and the blue. And then what we'll do is we'll graph the other one. So I'm going to show you a different technique here. I mentioned the technique of putting this into slope-intercept form, which you certainly could do here. Another technique is to use the x and y intercepts, because sometimes those x and y intercepts are really easy, nice to handle points. So what I mean by that is that if we're looking for the x-intercept, we know that y is 0. And so if you just look at your problem and say, okay, y is 0, well, 2x is equal to 6, that means x must be 3. So it's really fast, many times, not always, but it's really fast to get those values. And then if you look at the y-intercept, that's going to be when x is 0. So again, you can let x be 0 and y must be 6. So again, very fast, and it allows us to quickly grab, all we need is 2 points. So quickly grab 2 points. X is 3, y is 0. That is going to be 1, 2, 3, that's here. And 0, 6, 1, 2, 3, 4, 5, 6. And look at that. All we have to do now is just attach those together with a solid line, which looks like that. So that's going to be 2x plus y equals 6. And you can see then, once we shade this final one, y is less than or equal. You can do a test point if you'd like. And I'm sorry, this is not showing up super well, but it's hopefully good enough for right now. I'm going to go ahead and shade in the feasible region in black. So the feasible region is right here. The overlap of all of those looks like this. And it's pretty easy to see our intercepts, I hope. So you have, let's see, 1, 0, and you have 3, 0. And this last one here, again, you want to make sure that you're really precise on your slope in order to figure out where that point of intersection is. But I have 1, 2, 3, and 4 as my final vertice right there. Okay, let's try another one. This one's going to be a little bit more extensive. So let's start with our first one. So here, I'm going to take that same approach and identify my x and y intercepts because I think it will just be easier than trying to rearrange everything. So if x excuse me, if y is 0, so again, you kind of cross this bit off, then x is negative 1/2. And for my y-intercept, I know that x is 0, and let me go up here and erase this part. So if x is 0, then y would be positive 1. All right, I'm going to take a look at the other intercepts here because I'm wondering what our scale should maybe be. We might want to adjust our scale to make a little bit more sense. Okay, here it's pretty simple because there isn't really any number being multiplied by x or y. So I have 4, 0 for my x-intercept as well as my y-intercept. And then for our last one, sort of limited on colors, I apologize. So for my last one, I have my x-intercept. That is, again, when y is 0, so x must be 4. And for my other one, so I have my y-intercept, which is 0 and 1. Okay, when we graph this, because of that x-intercept of negative 1/2, I think what I'm going to do is make my grid, kind of tweak the scale of my grid, because none of these values are very large. And so I think it's much easier for us to probably double our grid. So in other words, if we just let this be 1, and then 2, and then 3, and then 4 like that, and kind of do that across the board, that will help us graph this a little more effectively. Okay, let's start with the red one. So x has an intercept, the graph has an x-intercept of negative 1/2, which is here, and y-intercept of 0, 1, which is there. This is a solid line. Now we could continue to put points here if that's helpful. Remember, if you keep your slope consistent, the slope is clearly up 2 over 1. We could plot as many points as we want on the grid, and that very well may help us identify exactly where this region or the feasible region will intersect in terms of the 3 constraints that we have. For our other one, we have intercepts of 4 and 4, and you can see that the slope here would be just simply 1. So you would continue in this, negative 1, you would continue in this pattern of a slope of negative 1. And this one is also solid, which looks like that. Sorry, that's a little wobbly. And then we have our last one. Notice I'm not shading anything yet, okay? So our last one is going to have an x-intercept of 4, 0, which is a nice intersection right there, and a y-intercept of 1. Okay, this one has a more distinct or drastic slope of 1/4, so we would have points like that. But you know what? We've already found our points of intersection, so I don't really have to worry about the in-between there. Okay, so that's what we have. Now we're going to shade. When you shade, the neater you can be, the better. So with the red one, this is a little bit tricky because when you look at the problem, it says y is greater than like that, but notice that there's a negative here that will impact how we shade. So I would highly recommend taking a test point. Notice how with the red graph, we actually don't intersect 0, 0. So I would think about 0, 0 for this first red graph and figure out if 0, 0 works or not. So I would plug in 0, 0. So I have 0 minus 0 is less than or equal to negative 1, and that's our question. So is 0, did I say less than? I meant greater than or equal to 1. So is 0 greater than or equal to negative 1? And the answer to that is yes. So in this case, we would actually be shading the region with 0, 0. And that's where some of the shading can get really confusing. So again, those test points I think are really helpful. All right, so my red graph will shade like this. And you can certainly have shaded as you graphed it. I just kind of saved everything until the end. Okay, with the blue graph, again, we have x plus y is less than or equal to 4, and so we could do the same thing. I'm going to kind of just walk through it verbally. So if we test 0, 0, we get 0 is less than 4. That is absolutely true. So I'm going to shade the region with 0, 0. It's going to be here. And then for our last graph, I'll do the same thing because 0, 0 is not part of the line. So is 0 greater than 4? And the answer to that is no. So I'm going to shade opposite 0, 0. And again, you can see how quickly this gets messy. But this is our feasible region right here, this overlap. And the vertices of this feasible region are 0, 1, and 4, 0, and 1, 3. Okay, that concludes the first lesson in linear programming. So this is our skill base that we need to form in order to analyze these problems. Now, we'll do a lot more real-world problems where we'll have real-world data, but in the case of graphing these things, it's really important that we get a sense for how to shade, where the feasible region is, and how to find the vertices. Thank you.